So you're saying World War II was more dangerous than an alien invasion?
Yeah, you guys have it easy here. Low-key Ultron? We had trench foot.
But alien technology is far more advanced than anything from the 40s.
Yeah, and when was the last time someone died to a laser blast? Worst thing it does is knock you out. Try saying the same thing to a 9mm from a Luger PO8.
You sure know a lot about German pistols.
I have a complicated history with Hydra. Cool story, Rogers, but everyone knows going quantum makes the Germans look like the French. J'adore!
How did you escape the quantum world?
I'll tell you how. Through bullshit!
Wow, Stark, you kiss your mother with that mouth? Probably not, because she's dead. Zing!
Hank, you should have disappeared in the quantum world. You should have literally stopped existing.
Could someone explain why? I'm too attracted to know about this stuff.
Certainly, Nat, but let's just say at the offset that it's all nonsense. No one actually understands quantum physics. We just saw the math works, then made shit up. If anyone tells you otherwise, they're a filthy goddamn liar. Especially on the internet.
You're not gonna talk about my regular shrinking? Just going straight for the quantum? Stark, you slut.
Nah, lots of people can shrink. We'll save that talk for Wasp.
I'll be dead in the ground if Wasp gets one of these videos before me.
What does quantum even mean? It just feels like a buzzword at this point.
Great starting point, Nat. In the world, some things are quantized, meaning they come in discrete units. Take money, for example. It's quantized to 1 cent. You can't have a coin worth less than that. Well, the same is true for certain physical properties like energy and charge. Turns out these things are also quantized, and that's essential to how nature behaves at very small scales.
Are you on booze, Stark? Energy doesn't come in steps, it's continuous. A cheetah, a jet, cracking a beer open off Bucky's perfect abs. The energy for all these things is completely different.
It's a weird concept, I know. In fact, the guy who discovered this didn't even believe it at first.
Who discovered it? I bet it was Dr. Doom.
Dr. Doom isn't even a real doctor.
Really?
He was expelled for talking to the dead and for being ugly. He do be hideous.
The guy that discovered energy's quantized was Max Planck, and the value of each quantum of energy is named after him. A wave's energy comes in discrete packets equal to Planck's constant times its frequency. Planck's constant is equal to 6.626 times 10 to the minus 34 joule seconds. So yeah, each quantum of energy is incredibly small. That's why we don't notice it in our everyday world.
Interesting, but how does this explain why the quantum world's so dangerous?
Well, before we even get that small, let's think about what the world would be like at the atomic scale. Okay, thought about it. You'd be dead.
Everything's always so dramatic with him. Well, that's funny, because I feel pretty alive, Stark.
Oh yeah? And how did you deal with all the photons firing left and right? It would have been like the middle of a battlefield.
Photon? What's that, a new type of German pistol?
Do you have PTSD?
PTSD's nuts!
No, we're not doing this. We're not doing this stupid joke again.
A photon is a particle of light. Atoms are constantly absorbing and emitting them. Each photon has energy equal to Planck's constant times frequency. That formula we saw earlier. The energy's small, but at the atomic scale, so are you. It'd feel like a bullet.
Why do atoms fire them so much? Are they getting a little excited?
Oh, Nat, you tease.
Actually, excited is the correct word for it, but it's not the atom. It's the electrons. Atoms have a bunch of electrons, right? And they can only be at certain levels of energy since energy's quantized, you know? So when an electron goes from a high energy to a lower energy, what happens to the energy difference? Well, it gets emitted as a photon. And if an atom absorbs photons, then its electrons get excited and jump into higher energy levels.
Stark, you little whiskey goblin. You haven't told them that photons are massless. That's why they didn't kill me. I couldn't even feel it. Kind of like your ex-wife's love for you. Hey, Ant-Man, I have crippling depression.
Yeah, that's true. Photons have no mass, but they still have momentum.
Okay, well, I know enough about physics to know that makes no sense. To have momentum, you need to weigh something.
Wasp didn't know that. Does that mean she's more attractive than you?
No, Rogers, that means she's an idiot.
You're only half right, Nat, and that's the half calling Wasp an idiot.
I sure hope she doesn't show up at the end of the video.
But photons do have momentum, and it's equal to Planck's constant divided by wavelength. This is actually more of a consequence of special relativity than quantum weirdness. Photons are particles of light, and so they move at the speed of light, which is when special relativity kicks in. For visible light, a photon's wavelength is around 500 nanometers, making its momentum approximately 1.33 times 10 to the minus 27 kilogram meters per second.
That's still an absurdly small number, Stark.
Not getting it yet? Fine. Let's talk about pressure. At this scale, Ant-Man's cross-sectional area is tiny. Pressure is the force per unit area, so if that area is small, then the pressure is going to be enormous. If Ant-Man shrinks to the size of a hydrogen atom, then his radius would be 5 times 10 to the minus 11 meters. We can model him as a sphere, meaning his surface area will be 4 pi r squared, which comes out at 3.14 times 10 to the minus 20 meters squared. Now let's assume a photon hits Ant-Man and transfers its momentum in a femtosecond, which is 10 to the minus 15 seconds. Pretty common in the atomic world. And the force Ant-Man experiences is equal to the momentum divided by time, which is 10 to the minus 12 newtons. And the pressure is equal to the force divided by area, which is 10 to the 7 newtons per square meter. That's 100 times atmospheric pressure. Now imagine a whole stream of photons. You see why he should be dead?
Wow, Stark, you sure do yap a lot.
You're a scientist, Hank. You should already know this. What the hell is wrong with you?
How about the fact that my daughter doesn't love me?
You know what? Forget I asked. The point is, you would literally be getting punched by light. It would be ripping away your electrons. You'd become unstable. You'd be falling apart molecule by molecule.
Well, maybe he's just good at running away from things.
No wonder his marriage failed.
We sure are unpacking a lot of emotional trauma today. I mean, sure, it's unlikely for him to dodge the photon bullets, but it's not impossible, right?
Actually, it is impossible due to electronegativity.
What's electronegativity?
A sad version of electropositivity.
Was that a joke?
It's when atoms trap you. Some atoms are thirsty for electrons. They're constantly trying to attract them. That's what most chemical reactions are, just a transfer of electrons between atoms. And one of the scariest of them all is oxygen. It's highly electronegative, craves electrons, will do whatever it takes to get them, will localize you in a potential well just for a taste.
Without consent?
Oxygen doesn't ask for consent.
Dear God.
Oxygen is one of the most electronegative atoms there is. It's small, meaning it has a high nuclear charge. Its nucleus really wants to pull electrons towards it. Ant-Man's tasty little body is full of them.
My eyes are up here, Stark. How does it pull him?
With tentacles!
Anime is real!
Just kidding, it's an electrical force. Electrons negatively charged, nucleus positively charged. But once it gets you, you're gonna be stuck there until you get enough energy to break free. Gotta pray that a photon hits you so that your kinetic energy can overcome oxygen's potential energy. Assuming, of course, the photon doesn't break your neck.
Well, you had me convinced. Ant-Man should be deader than the MCU after Endgame. That was low-hanging fruit, Rogers. Okay, well, how about this? Ant-Man should be deader than his chances of his daughter forgiving him when she's older. Love it!
So are we in the quantum world now?
We are, and you're probably wondering about wave-particle duality, right?
Actually, I was wondering if Rogers had a homoerotic relationship with Bucky in the 1940s.
Nat, we all know the answer to that. But yes, light. It behaves as both a wave and a particle, and it's not just light, but electrons and protons too. In fact, every moving particle has an associated wavelength equal to Planck's constant over momentum, also known as the de Broglie wavelength.
There's that damn H again.
Yep, it shows up everywhere in quantum mechanics, and it's a good thing it's so small. If we calculate the wavelength for a 1,000 kilogram car moving at 20 meters per second, we get a wavelength of 10 to the minus 38 meters. So absurdly small that it's effectively zero. That's why objects in the everyday world don't behave as waves. But what about an electron moving at 1% the speed of light? Well, using the same formula, we get a wavelength of 10 to the minus 10 meters, which is much bigger. That's around the scale of atoms, so the math checks out.
What about Ant-Man when he shrinks? He keeps the same mass, so how would that affect things?
Glad you asked, Nat. You're quickly becoming my favorite Avenger.
I must kill Black Widow.
Assuming Ant-Man weighs 80 kilograms and jogs at 1 meter per second, his wavelength comes out at 10 to the minus 36 meters, which is so small it breaks physics.
Stark, you absolute bastard of a man. The car had a smaller wavelength than that.
Yeah, but physics doesn't care because we're not attempting to treat it quantum mechanically. You, on the other hand, are a quantum particle, and you're even smaller than the Planck length.
This Planck guy again, really?
Yeah, he was kind of a big deal. German physicists tend to do that. But what is the Planck length, I hear you ask?
Stark, that's just the echo inside your helmet.
Well, the Planck length is this: the square root of h bar times g over c cubed. It works out at around 10 to the minus 35 meters, which is bigger than Ant-Man's wavelength, which is a massive problem because the Planck length shouldn't be bigger than anything.
Why not?
It's the smallest meaningful length in physics. Below it, space-time breaks down. No coordinate system is well defined there. Nothing can measure it. It's smaller than space itself can represent. He should cease to exist, just disappear. His wave function should lose meaning.
Wave function?
Okay, you've done well to make it this far, but we're gonna get into some wild territory here. I'm about to show you something deeply unsettling, traumatizing even. If you're squeamish, then please, look away.
Rogers, what should we do?
Are you also feeling a spark between us? Because, listen, about that whole Bucky thing.
It's the Schrödinger equation!
My eyes!
I thought the Germans lost! I thought the Germans lost! It looks like my ex-wife!
Wait a minute. Wrong one. Here's the time-independent Schrödinger equation.
That's still horrifying.
Stark, what the hell is wrong with you? Are you still mad I beat you in Civil War?
Totally kicked your ass, low diff, but no, this is a very important equation. It's basically the rule book for how things behave in the quantum world. It tells us how a particle's wave function evolves, and it's a balance between two things: kinetic energy and potential energy. If the wave function sharply bends, then it has a lot of kinetic energy. And if it's affected by gravity, an electrical field, or stuck in a potential well, then that's what the potential energy tells us. It basically describes the particle's environment. So really, all the equation is saying is that a particle's total energy is equal to its kinetic energy plus its potential energy.
I guess that's not so bad.
But there's a massive problem! When Ant-Man shrinks, his mass stays the same. You can see that the kinetic energy term in the equation is divided by m, the mass of the particle. In Ant-Man's case, m is massive, so he will have very little kinetic energy compared to much lighter particles, like electrons and protons. This means he becomes tightly localized, super easy to trap in potential wells like the oxygen atom we talked about earlier.
And super easy to trap in loveless marriage. Gosh, how many times are we gonna fucking repeat this same joke? Huh? How many, guys?
That's why he should have never been able to escape the quantum world. Well, unless he used quantum tunneling.
Do you still need us to prompt you for your next explanation, or are
In
you...
quantum mechanics, particles aren't in a specific place until you measure them. Before you measure him, Ant-Man is described by a wave function, the Schrödinger equation. This only tells us the probability of where he might be. The moment we try to look at him, his wave function collapses.
Don't say it. Say what? You were gonna say collapsed? Like Ant-Man's marriage or some shit? What? No. It's not easy being nice all the goddamn time, alright?
This is known as the measurement problem in quantum mechanics. You try to measure something and it changes. It's profound and really annoying. The transition from quantum superposition to definite reality. This is why Schrödinger's cat is both dead and alive.
I thought it was dead or alive.
Common misconception, it's actually both until you look in the box. Told you quantum mechanics was weird, right? But even after the wave function collapses, there's another problem. There are limits to what we can know about the particle. The more precisely we know where Ant-Man is, the less we know about how fast or which direction he was going in.
You probably went to get milk, am I right? Rogers, I'm going to crawl up your anus and enlarge myself.
Oh, Bucky will be jealous.
The limits to which we can know both position and momentum are defined in Heisenberg's uncertainty principle. Delta x is the uncertainty in position, and delta p is the uncertainty in momentum. Our old friend Planck is back. delta x times delta p is always greater than or equal to h bar over 2. You guys see how crazy this is? Like imagine trying to cross a road, and if you see a car, then you can't know how fast it's going. Or if you know how fast it's going, you don't know in which direction. Imagine how dangerous the quantum world is because of this. Electrons zooming by, who knows where, at fractions of the speed of light.
Okay, but how does this help Ant-Man? You said his mass is so big that he has no kinetic energy and falls into wells or whatever. That his only hope of escape is the energy from a photon, but the momentum might kill him. And now because of Heisenberg, he doesn't even know where he's going? He's more doomed than Avengers Doomsday guest starring Dr. Doom.
He can't fight his way out of a potential well, but he can tunnel out of it. In the everyday world, if you run out of energy, you can't do anything. Imagine climbing a steep hill and getting tired. You just gotta stop and rest. But in the quantum world, you can do things you're not meant to be able to do. If you don't have the energy to break through a barrier, you can still do it.
I'm sick of your lies, Stark. All you do is lie.
It's not lies, it's tunneling. Here's the last equation I'm going to show you. The probability of tunneling through a barrier. T is the transmission probability. It ranges from 0 to 1. K is the decay rate of the wave function in the barrier. The bigger it is, the less likely you are to tunnel. If the barrier is very wide or tall, then it's harder to tunnel through it. If the particle is heavy, it's also more difficult, but the more energy the particle has, the easier it gets.
I wish I could tunnel my way into my daughter's heart.
That was beautiful, Hank.
I guess love was the real quantum mechanics all along.
No, quantum mechanics is the real quantum mechanics. You're an idiot. Anyway, let's do an example. Nat, how much do you weigh?
Excuse me?
60 kilograms, great.
Who ate all the shawarma, Nat?
Hulk!
Oh yeah, fair point.
Nat is going to walk through a 1-meter wall with a potential energy of 1 electron volt. Her transmission probability is approximately e raised to the negative power of 10 to the 25. This is an exponentially small number, basically 0, so she doesn't get through the wall. But how about we do the same thing for an electron? Well, in that case, the transmission probability is around 10 to the minus 50. Small for sure, but definitely not 0. In fact, trillions of electrons try to tunnel all the time, so it happens constantly.
That's really cool, Stark, but what about Ant-Man?
I hear you, Nat. Ant-Man weighs 80 kilograms, so if we do the same calculation for him, and it's 0.
What?
Yeah, his mass is way too high. It's approximately 0.
But I thought the whole point of this was to show he could escape.
Nah, I just wanted to yap about quantum mechanics for 10 minutes straight. Can't believe I got away with that.
But what about pin particles? Won't they help?
I don't know.
You don't know, but you're meant to be smart.
Smart people don't understand quantum mechanics, and neither do stupid people. It's only the people in between, you know?
What a depressing way to end our conversation.
I'm wasp through the wasp, but I prefer wasp.
Shut up, Janet!